Okay, hello everyone and welcome to Chem 1331. Before I start, I'm going to take a moment to admire how full the classroom is because it will never be like this again. So it's great. We are going to, before I get into chemistry stuff, you'll notice, you may have seen it already, there's an announcement on here about a meeting for HOSA, which is one of our many pre-health organizations. If you are part of a student organization and you'd like to advertise your organization before class, just let me know. I'll have these fairly regularly. So this was the first one to contact me. They have a meeting tomorrow in Agnes Arnold. It's for anyone who's interested in pre-health careers as far as I know. All right, with that, we need to get into what we're doing today, which is going to be mass laws and atomic structure. Because of the snow day, the unexpected weather event that we had, I won't be able to go through a full outline of the syllabus, so you're going to get a little bit less of the always enjoyable syllabus day than you normally would. But I do want to highlight a few things about the course, just so you're all aware as we get started, so there's no confusion during the first week, as there often is. The first thing you should be aware of are the homework assignments. We don't have any currently available. No, I think the first one may have just opened. Sorry, strike that. Anyway, the first one is available. They always become available Sunday at midnight, and then they will be due exactly 1 week later at 11:59 p.m. So there will always be 1 week to complete each homework assignment. You have 4 attempts, and your highest score counts. So I encourage you to use most, if not all 4 of those attempts in a given week to help you practice the material. Be careful if like most of you choose to do the homework assignment on Sunday, the day it's due, which is a common practice. Be aware that there will always be on Sunday 2 homework assignments available, the one that is due that same night and the one that just opened up for the next week. So make sure you do the correct one and not the one that's due the following week if you need to still do the previous one. So just be aware of that. Look closely at the chapter numbers and the due dates on those so you don't get confused. Exams, which will be something we'll tackle much later on, obviously. We have 3 midterms and 1 final, unless you will take those in CASA, just like you've been doing for the PA test, so get used to that procedure. And to clear up a common misconception, there are no dropped exams in this course, so all of them count. All right, your lone incentive for coming to class, besides listening to me, are the bonus quizzes. So they're going to be periodically given in class. They will be unannounced. I'm not going to know exactly how many I'll do just yet, but usually on a typical semester it's on the order of 6 to 8. And each quiz is worth 2 points, so you get 1 point if you're here and you actually just try to do the quiz. As long as you put something down, you'll get that point, so you get half of the credit, and then you get the rest of the half of the credit if you actually get the question right. This time, because I've had so many complaints about clickers in the past and I don't use them a lot, we're not going to do anything with clickers. So I'm going to torture myself and do written bonus quizzes. And so you have to get credit for the bonus quiz, though, please print out the bonus quiz form that's posted in Blackboard. You'll find it amongst all the other course content. So bring a few of those with you every time in case we need to use one. They're half sheets, so you can tear the page in half. And that'll just make it easier for me to collect them and to grade them ultimately when I have to do that by hand now. So they will be on paper this time, since last year I used clickers and we didn't really use them very much and most students thought it was a waste of money. Okay, and then how do we calculate your bonus total? So you can get a maximum of 2 bonus points in this course added on to your final grade. So it's not that each quiz is 2 bonus points, it's that your total conglomerate score will be scaled to 2. Meaning out of the 100 points that are available in this course, or the 100% of your grade, you can add on 2 to that based on your quiz performance. If you get every single quiz question right, you get 2, and then it goes down from there. So as an example, let's say we do 6 quizzes, and you got 8 out of the top 12 possible points on those quizzes, meaning some combination of showing up and getting questions right yielded you 8 points. If that's the case, then we divide that. We would average that out to give you 1.33 bonus points on your final grade. So that's an example of how we calculate that. So a lot of times at the end of the semester, people mistakenly or optimistically believe that each bonus quiz is worth 2 points. In reality, it's 2 points total. So not a huge incentive, but something to hopefully spur your attendance a little bit. The other thing I encourage you to attend regularly are office hours. I'm going to have these every day from 12 noon to 1 p.m. Now when I say those are my office hours, that doesn't mean that's the only time I'm in my office. It's just that during those times I can all but guarantee I'll be there, except in rare circumstances that I'll let you know about. If you're able to come during that time, it's very helpful to have people come with questions during those hours. If those times don't work for you, if you had a more private matter you wanted to discuss where you didn't want other students eavesdropping, You are welcome to come at any other time. I'm in my office most of the time, and the safest thing for you to do would be to email me ahead of time to set up an appointment to make sure I'll be there at whatever time you want to come. So I am flexible with this, but these are the times where I will, barring any, important thing going on in my life, I'll be sitting in my office during those time periods, and I encourage you to take advantage of those regularly. The students that typically do the best in this course, they're the ones that put the consistent weekly effort in. So it's not that I'm the magic chemistry whisperer that can cure everything that you're having trouble with, but if you're putting that regular, consistent effort into the course and coming to my office hours regularly and using all the other resources outside of class, that's going to help you succeed. So I had a much longer pep talk than that planned, but because we have to move on, we won't have time for that. And as you'll find, there's a reason why I'm a chemistry professor, not a motivational speaker. But you should utilize all the other resources besides office hours. We have the homework assignments are good practice, the textbook. I'm going to be posting all the lectures on YouTube. That's one thing I forgot to put on here is the YouTube channel. Many of you have probably found it, but if you haven't, all of the lectures will be posted to YouTube. And I recently qualified for a custom YouTube URL, so that was a proud moment in my YouTubing career. So it's easy to find now. And like I said, all the lectures will be posted there. Every week after the homework assignments are due, so on Monday morning likely, I'll be posting a homework review video where I'll go over the homework questions from the previous week that were the most difficult. If you have any requests for what you want me to go over, please send those to me, but I'll primarily just look at the results of the homework and decide for myself. We'll have exam reviews that will be posted here, and that's going to be primarily the bulk of it, but a lot of students use that resource as well. Now, I don't think it's a good substitute for showing up for class, because if you're watching, I get a lot of views on my YouTube video, but the average one is about like 2 minutes. So I know that not a lot of people are actually sitting through and watching the whole thing. So it's better to come to class, but this is a good backup resource if you have to miss class or you want to review something that I went over and you didn't understand. All right, with that, if you have any other questions, please just send them to me or ask me after class, but we need to move on to the material. So we're going to start in chapter 1 in the book if you're following along with the textbook. So there is a review chapter, but we won't be covering that, but I did post some notes on that to help you study if you need to. But we're going to be starting in chapter 1. And one thing we want to start out with and hope to understand is what's called the scientific method. So this is something you'll deal with more directly in the lab class, which I'm not really involved with. But keep in mind, we're going to be teaching a lot of scientific laws and theories in this class. We'll talk about what exactly that means, and all of those came from the scientific method. So every piece of knowledge that you're going to acquire in this course that I'm going to try to help you learn is something that someone in the past used the scientific method to figure out. So this is kind of the driving force for all scientific discovery, and it's really based on 3 key ideas here: observation, hypothesis, and experiment. So simply put, an observation is something you sense or measure. There are 2 kinds of observations. There are qualitative and quantitative. All right, so there's qualitative and quantitative measurements. Qualitative ones they're the ones that are more, I guess, subjective or more based on your senses. So, for example, the sky is blue is a qualitative observation, or Professor Teese looks strange. That would be another qualitative observation. And then quantitative ones are ones that are more commonly used in scientific discovery. Those are ones that have numerical values associated with them. So, if you said, this piece of metal has a mass of 1.23 grams, that would be a quantitative observation. It's going to have a number and a unit associated with it. And those are both important, though. It's not to say that one is more important than the other, but we use both of those in chemistry. So when you're starting out and trying to learn something about science, some new scientific principle, you start with a series of observations. And then from there you develop a hypothesis. So a hypothesis is a possible explanation for observations. So you observe something and you want to say why it is. Now, generally speaking, a hypothesis is based on flawed or limited information. All right, so you don't have everything you need to be able to come up with a conclusive scientific theory, as we'll get into in a second, but it's something that may potentially explain what you're observing. Okay, so it's a possible explanation, usually based on limited or flawed info. And that's kind of the starting point. It's what you think might be true, and then your job as a scientist is to prove whether or not that is or is not true. As an example, they might be familiar with the sort of common folklore tale of discovering gravity, where Isaac Newton had an apple fall on his head. Whether that's actually true or not, you could imagine that the observation was that the apple fell from the tree onto his head, and then his hypothesis, he probably wasn't this ridiculous, but his hypothesis might have been, well, the tree is throwing the apple at my head. That might have been his hypothesis for his observation. Now, clearly that's not correct, but that is a starting point, and then from there he would design experiments to test that. So experiments are designed to carefully test your hypothesis and rule out what is right, or determine what is correct and rule out what is incorrect. So if he had started, testing other fruit trees, he would find that fruit also falls from them. He would find that other objects besides fruit fall, that you don't need a tree there for an object to fall. All these different ways of testing his initially ridiculous hypothesis to narrow down on a more plausible explanation. That's what an experiment does. And then what your experiment is going to involve a lot of observations. So as you do your experiment, you collect a whole bunch of new observations, and those lead to new hypotheses and new experiments, and the cycle continues on. Not quite as majestic as the circle of life, but it is very important nonetheless. So we have this kind of process repeating over and over again, and this leads to sort of two parts of scientific knowledge that we're going to talk about in this course. So one is a law, scientific law, and this is a very definitive description of what happens. All right, it doesn't explain why it happens, it just tells you what happens. It's a repeatable set of observations that you can be very confident is going to occur in a given set of situations. So going back to the gravity example, the law of gravity is that an object with mass will fall to the earth with the force of gravitation is mass times gravity times the height or acceleration, all those things. I'm forgetting all my physics. But anyway, the law of gravitation is the one that says what happens when two bodies attract each other gravitationally. And then what you also need in science is a theory, which is what explains it. And this word theory is one that's very often misused in sort of the popular literature. A theory is not just a random guess. It is an explanation for a whole bunch of observations which constitute a law. So then there's also then the theory of gravitation, which is even took even longer to come up with. And that was, Einstein and gravitational waves and things like that people are still debating to this day. So what often happens is laws are more or less incontrovertible. We know what happens when two objects with mass are near each other and the force of gravity that exists between them. We know that with certainty. But then why does that happen is perhaps a more open-ended question that often gets refined as more and more experiments are done. So theories evolve over time. Laws generally are fixed and pretty solid. So we'll talk about laws and theories today, so we want to understand the difference between those as it applies to science in general, especially in chemistry. Now, as we go in and start talking about laws and theories associated with chemistry, we should first understand what exactly chemistry is. So what are the types of things that chemists are interested in? What types of laws and theories are we coming up with? So chemistry is the study of matter. So that's kind of at the top. And within matter, we have a few different important classifications and subclassifications. And we're going to talk about both of them. Primarily at the beginning of this course, we're going to talk about what are called pure substances. All right, so matter has two different types. One of those is pure substances, and that's what we're going to spend a lot of time on, especially at the beginning of the course. Pure substances are defined by constant composition, so we're going to talk in more detail about what composition means and all that, but pure substances have constant composition, which means if you take a pure substance from this side of the world, compare it to the same pure substance from the other side of the world, they're going to have exactly the same composition, chemically speaking. Now, the other major classification of matter are mixtures. Now, mixtures are important too, and somewhere around Chapter 6, I think it is, we'll talk a lot about chemistry that happens in mixtures, a certain type of mixture in particular. And mixtures have variable composition. So there is no fixed composition associated with mixtures. An easy example to know the difference between a pure substance and a mixture: water by itself is a pure substance. And as you likely learned at a very young age, water has the composition H2O. You can collect water from Galveston, you can collect water from the North Pole, and it will always be H2O. And then if you had salt water, though, that would be an example of a mixture. It's salt mixed with water, so it has two different substances present, two different pure substances present. And the composition can be different depending on whether you collect it from a natural source, whether you prepare it yourself by dissolving salt in water. You can dissolve 1 tablespoon or 2 tablespoons in a glass water, so on. So mixtures have variable composition, and they compose of at least 2 different pure substances, sometimes more. Now within each of these categories, mixtures and pure substances, we have additional subclassifications that we're going to talk a lot about in this course. So there are 2 types of pure substances, and we will talk a lot about both of these, especially early on. We'll get right into them. So one are called elements. And these are substances that cannot be broken down further into simpler substances, at least not by chemical means. All right, so that's sort of the simplest substance. And then when you combine more than one element together, 2 or more elements together, you get what are called compounds. Now these are still pure substances, so every compound is going to have constant composition, H2O being an easy example that we've already talked about. And really the whole essence of chemistry is interconverting elements and compounds using chemical methods. So we're studying transformations between elements and compounds, or between one compound and another compound, and so on. So there's, this sort of interplay between elements and compounds happens all the time in chemistry. Compounds are, again, just to reiterate, a combination of elements. So it's 2 or more elements together. So those are the 2 types of pure substances. And a lot of the early stuff in chemistry that we'll talk about involves both of those. And then in terms of mixtures, we also have 2 types of mixtures, and we will primarily only talk about the first of these 2. So the types of mixtures are classified as homogeneous and heterogeneous. Or some people say homogeneous and heterogeneous. All right, so those are the 2 types of mixtures, homogeneous and heterogeneous. And really the difference between those, you can almost tell by looking in most cases. So a homogeneous mixture is what we call a single phase. In other words, you can't tell that there's 2 or more things mixed together. Salt water being a great example of that. If you look at a glass of pure water next to a glass of salt water, you can't really tell the difference just by looking at them. You can't tell that there's salt and water in there. The 2 phases are mixed completely together to give you a single phase homogeneous mixture. And then in heterogeneous mixtures, you have visibly distinguishable parts. Sand being an example of a heterogeneous mixture, where you can see the different colors of the different minerals that make up sand. We're not going to really talk a lot about heterogeneous mixtures in this course. They're not a topic that is particularly important to chemists most of the time, but that is one of the categories of mixtures that we'll see. All right, so this is sort of a breakdown of what chemistry is and what chemistry is the study of. And before we get into some of the early chemical discoveries and chemical laws, let's talk about, at a microscopic level, the classification of matter. So this is stuff we're going to get a lot more details on as we move forward. But we just want to get a very basic appreciation for it before we start, which is if we had the world's most powerful microscope and we could zoom in on different types of matter and look at the fundamental particles that make up those matter, which, as we'll learn very soon, are called atoms, and then those atoms can combine to make molecules, what would they look like for the different things? So if we zoom in on an element, there's only going to be one type of particle present. So assume that each different particle we're looking at has a different color. That's the way we're doing it here. So if you zoomed in on elements, they would just have one type. They could either be a single particle by themselves, or 2 of the same particle, or 2 or more of the same particle kind of connected to each other via a chemical bond. But you would only see one type of fundamental particle if you looked at an element by itself. Keep in mind, again, that elements and compounds are the ones that we call pure substances. So both of these 2 here are the pure substances that we just talked about. If you looked at a compound, the difference would be you would have two different kinds of elements, or possibly more than two. So you see here you'd have a red one, or I guess magenta combined with blue, or you'd have different ratios possibly, magenta combined with 4 black ones. But if you look at a pure compound, there's only one type of particle, as we call them molecules. Each one has the same exact composition, but there's two different types of elements present. So that's the difference between elements and compounds. And then if you go to mixtures, you would see a combination of those two things. So this would be a mixture of elements. You have red and blue elements together. This one over here would be a mixture of compounds, because you have two different kinds of compounds. This one with the magenta and blue, this one with the magenta and the 4 blacks that we talked about. So this would be a mixture of compounds. So mixtures can have any combination of pure substances as their constituent parts. When you have a mixture, it can be a mixture of elements, a mixture of compounds, a mixture of elements with compounds, and all those different possibilities. So this is the difference between pure substances, which only have one type of particle, fundamental particle, and mixtures which have more than one type. But of course we're leaving out a lot of important details that we're going to start getting into by the end of it today, and what are the exact structures of these and how do we distinguish them from each other. Alright, so to get into some more things about early chemistry, we do want to have a little bit of appreciation for the history of chemistry. This is not a history course, and we're not going to do much outside of this first chapter dealing with the names of people that made discoveries. But we do want to have a little bit of a sense of where do these things come from, and how do we sort of lead into this modern, very mature field of chemistry that we're going to be studying in this class. So the first people to think about chemistry or at all, though they probably didn't call it chemistry at the time, were the ancient Greeks. So they were making, they were observing chemical changes, at least qualitatively, by looking at substances changing colors and things of that sort, and they tried to explain them as best as they could, although without really the basis of the scientific method at their disposal. So they tried to explain chemical changes. It wasn't a particularly scientific approach, though. And they kind of had a much more simplistic view of chemistry, not surprisingly, since it was so many years ago, thousands of years ago. And they proposed 4 fundamental substances, which we now know is not really accurate, but this was their idea. And the 4 substances were earth, fire, air, and water. Now, if there's any other 90s kids out there, you may remember Captain Planet. Earth, wind, water. Heart was not one of the fundamental substances, though. But anyway, it's a lot like that. There's 4 fundamental substances: earth, fire, air, and water, which they kind of propose as being the basis of all matter, overly simplified. However, another idea that they had, although they couldn't really test this idea or had a very refined picture of it, was they were the first to propose atoms as fundamental particles. So they said that these substances must have some very small building blocks, and they called them atoms. Atom is from a Greek word, as it turns out. But they didn't have any real scientific evidence for that or any way to test that idea. They just sort of proposed it as being a possibility. And it turns out they were right, but they had no reason, they had no idea why they were right. So sort of the next era of chemical history came more during the Middle Ages, I guess you would say. Middle Ages and the Renaissance period, where you had this collection of scientists or pseudoscientists called the alchemists. Now, the reason I say that this is pseudoscience is because it was based largely on superstition. That doesn't mean they didn't make some important contributions. They made a lot of observations about substances, but they didn't have a very scientific approach to how they did this. And this era of chemistry spanned a long time, or at least 2,000 years, where people were doing what we called alchemy. And their key belief was that they thought they could change base metals, primarily lead, and they thought that they could change these into gold. So they're, like most people, they were motivated by becoming rich and thought that there must be a way to change lead into gold. It has to be possible. Now that's kind of the reason why this is branded as a pseudoscience, because science does not start out with an unfounded belief. Science starts out with a question that you then attempt to answer in a rigorous fashion using the scientific method that we talked about. These people just had their eyes on the prize and thought that some way, somehow, we would be able to turn lead into gold. So they made a lot of important observations about substances. They actually, even though they didn't realize it, they did some very important chemical reactions, but they obviously didn't succeed in their ultimate goal, because as we'll learn, this is not really possible to do. So it was sort of grounded in a flawed argument or flawed idea that you could turn lead into gold. They never got there, but they still made a lot of important contributions. Now, the first real chemists came around probably in about the 1700s or so. I don't remember the exact dates. And so Robert Boyle is very often credited as being the first chemist. So he was the first person that really made quantitative measurements on substances, and he was working with gases. So we'll learn about Boyle's law later on in the course, about halfway through or so. So he worked with gases, and he made a lot of quantitative observations. So he was sort of the first person to study substances in a very systematic and very scientific way. So we credit him with being the first chemist. And he proposed the concept of elements as well, these sort of fundamental substances that can't be broken down into any simpler substances. As we'll learn later on, Boyle primarily did physical measurements. He measured properties of gases like pressure and volume and temperature. The first person to really study chemical reactions in great detail was Joseph Priestley. So he's credited with discovering oxygen. And he systematically studied a lot of combustion reactions that involve burning something in oxygen. So he was kind of the first person to do careful studies of chemical reactions, which would be the process of converting one substance into another, which is something that hadn't been done before. So he made measurements, he made very careful observations, and learned a lot about how chemical reactions work, and he's often, another very important figure in early history. Now, what came a little bit later out of all of this, and sort of followed up by some other very prominent scientists, are the three mass laws, and that's kind of the real starting point for the concept we want to understand in this course. So the first mass law that we're going to deal with, there are three mass laws, as the title of this slide suggests. The first one is called mass conservation. It was formulated by Antoine Lavoisier, who, as you might guess, is French. And so let's look at a video that demonstrates the mass conservation. So let's see if I can pull this up. I still have it. Good. Okay, so what we have here is, I'll set the stage before starting this. You have sort of two flasks. You have a larger flask on the outside that has one liquid in it, and then you have a smaller tube on the inside that has another liquid in it. And what he's showing before he does anything, the total mass of this is 158.2 grams. Now let's see what happens. I should have turned this on off. Alright, so he has these two materials in here, and he's going to allow them to mix together at some point after causing a dramatic effect. And you can see clearly something happened. The color changed, it got cloudy, and substance formed. So we had a chemical reaction. Hopefully that's something we can all easily appreciate. And what he's going to do now is he's going to weigh the contents or mass the contents afterwards, and you see that it is still 158.2 grams. So we had this very obvious chemical transformation. The mass beforehand and the mass after were exactly the same. Okay? So that's, as we call, conservation of mass. I hope that doesn't mess up my video too bad because I wasn't muted there. Alright, so that's conservation of mass. And what it tells you, as you just saw, is that in a chemical reaction, the mass that you start with is equal to what you end up with. As we talk in more detail about chemical reactions in a little bit in this course, the substances that you start with in a chemical reaction are often referred to as reactants. Those are the things that you're reacting with each other. And the mass of those reactants in total is equal to the mass of what you end up with. So the mass of what forms. And those are called products. Okay? Another way that you've probably seen the law of conservation of mass formulated is that matter is neither created nor destroyed in a chemical reaction. Okay? So this is a very simple one, I think, but is often one that people forget about because it's so simple. So when you're doing, practice problems on the homework, even, for this chapter or even much later in the course, don't forget about the law of conservation of mass. If you, for example, let's say we want to make rust, which we know is iron and oxygen. If you mix, 6 grams of iron with 4 grams of oxygen, you can make 10 grams of rust. That's what you form at the end. So the sum of those two is going to equal what you're able to form at the end. So don't forget about this one. This was sort of the first mass law that people came up with. The second one we're going to talk about, which is a little bit more complicated, is the law of definite composition. So this one deals with compounds, which are, as we said, are chemical mixtures of elements. It was formulated by Joseph Proust. Possibly said that name wrong because it's not, I don't think it's, anyway, so it's the law of definite composition. We're talking about a given compound here. And that will always contain the same proportion of elements by mass. And another key point here is regardless of source. Okay, so as I already kind of mentioned earlier, if we were to collect pure water from Houston and compare it to pure water from Antarctica, the mass ratio of the two elements, hydrogen and oxygen, would be the same in both samples. So if you have a pure chemical compound, a pure substance that's made up of a chemical compound, the ratio of the elements will always be the same in terms of mass. So to give a slightly more complex example, let's say we had 44 grams of carbon dioxide, which all of you are furiously producing as you consume and metabolize all this information that I'm giving you. So if you have 44 grams of carbon dioxide and you analyze the sample, so carbon dioxide is carbon and oxygen mixed together in the compound, and that will contain 12 grams of carbon and 32 grams of oxygen. Okay, conservation of mass is obeyed. 12 plus 22 is 44, and this will be the ratio of those two, in this case the absolute amounts of carbon and oxygen that make up that sample. Now, an important parameter that comes out of the law of definite composition is what we call mass percent. And this is one common way of defining the composition of a compound, or at least the composition of one element in a compound. So if we have a compound that contains multiple elements, the mass percent is defined as the mass of a given element, whichever one we're interested in, divided by the total mass of the compound All right, now here's something that many of you got confused on the PA test and will continue to get confused on for the rest of this course. I sadly have to guarantee that. The difference between a ratio and a percent. So anytime we say percent, you have to take the ratio and multiply it by 100. Okay, so this would be the mass ratio, and then if we want to convert that to a mass percent, it has to be multiplied by 100. So that ratio mass of an element divided by the total mass of the compound is referred to as mass fraction. And if you want to convert that mass fraction to a percent, you have to multiply it by 100. Okay, so mass fractions will always be between 0 and 1. Mass percents will always be between 0 and 100. Okay? So if we do it for this example here, let's say we want to find the mass percent of oxygen in carbon dioxide. We use the numbers that were given to us. Our sample of carbon dioxide has 32 grams of oxygen. The total mass, as we said, was 44 grams, and then we multiply that by 100 to get a percent. So carbon dioxide is 73% oxygen by mass. So whenever you have the masses of each element in the compound, that's how you do it. And then the mass percent of carbon in carbon dioxide, we said there was 12 grams of carbon, 44 grams total, and that comes out to 27%. What you will notice, and what should always happen, is that the sum of all of the mass percents has to equal 100. Okay? So this time we only had two elements, so we have two percentages that add together to be 100. If our compound had three elements, we would have three mass percents to find for that compound, and the sum of those three would all have to be 100 as well. Okay, so that's what we'll see, and that's sort of the one some sort of quantitative concept that comes out of the law of definite composition. So let's look at some sample problems just to see how we use mass percent and how we calculate it. So this is another very closely related problem. So let's say we have a sample of pyrite, which you may know of as fool's gold, and it consists of iron and sulfur. So those are the only two elements that are in that compound, iron and sulfur. If we have a 50-gram sample of pyrite, it contains 26.7 grams of sulfur. What is the mass percent of iron in pyrite? So that's what this question is asking, is about iron. So we're going to learn a lot in this course, sort of the systematic ways to go through in solving problems. This is not a particularly complicated one, but as we go through the course, the types of problems we get are going to get progressively more complicated. And a lot of times, part of the challenge is sifting through the information you have and trying to determine what information you need to solve that problem. So the way that I like to start any sort of problem is write down what it is I'm looking for. So in that case, you usually go to the very end of the question and see what is it asking me. It's asking me for the mass percent of iron in pyrite. So as we just defined, the mass percent of iron is the mass of iron that we have divided by the mass of the compound pyrite times 100. So to solve this problem, we need two parameters. We need the mass of iron and we need the mass of pyrite. And so then we go and look at the problem and see what's given to us and what we need to find using other ways. So the first one that we can obviously see is the mass of pyrite is directly given to us as 50 grams. So we have that information right off the bat. We don't need to do anything else to find it. I'm going to move this down a little bit so I can solve the problem above. Alright, so the mass of pyrite is 50 grams. That's given directly in the problem. Alright, so try to sort through your given information, figure out what you already have, figure out what you do and don't need to solve the problem. Now the thing that we don't have right now is the mass of iron, but we are given the mass of sulfur. And this is where, as I said, don't forget about the conservation of mass law that we have, which is that the mass of iron plus the mass of sulfur must equal to that total mass of compound, 50 grams. So that means if we want to find the mass of iron, you have 50.0 grams of pyrite, and then we subtract out the mass of sulfur that part of that is consisted of, and that means we have 23.3 grams of. I won't write chemical symbols yet, so I'll confuse you guys. Okay, so we have 23.3 grams of iron. So once again, the sum 23.3 plus 26.7 equals 50. We were given this mass. We had to use a little bit of algebra to find the mass of iron. So this kind of combines conservation of mass and mass percent. And so when we plug the numbers in that we need, we have 23.3 grams of iron, we had 50 grams of compound, multiply that by 100, and so we get 46.6%. Significant figures won't be a huge deal in this course, but we should be at least a little bit mindful of them. So both of these reported measurements have 3 significant figures, so that's the proper way to report the answer. I will try my best to be consistent with that in class. It's not usually important when you do problems in Blackboard, but it's still potentially useful to know, especially for the lab course, and especially for Chem 2, where it becomes more important. All right, so questions on that one before I move on. All right, fairly straightforward application of the definition. Now let's see one other example problem of how we can use mass percent to do something a little bit more complicated. Now I'll give you a lot of problems in the notes. One thing I encourage you to do if you have time and the motivation is I'll post all these notes ahead of time, so it's sometimes helpful to go through the problems in the notes and see what you're able to do beforehand, or at least try them, or afterwards, alternatively, you can go through and try to solve these problems yourself, whatever you think is best for you. But I do have a lot of problems in the notes, and we'll go through them in class, but you're encouraged to look at them before and after as additional practice as well. Anyway, going back to pyrite, so we have the same information we were given before. 50 grams of pyrite contains 26.7 grams of sulfur. But now we want to know how many grams of sulfur are in a 1.235 gram sample of pyrite. So instead of a whole 50 gram chunk, we have just a smaller chunk of 1.235 grams. How much sulfur is in there? And so what we're going to do for this is we're going to set up a conversion factor. So when I solve problems like this, I always start with what I'm looking for. I'm looking for the mass of sulfur in that sample. So in grams, this is what the units are that we're working with here. And then we start with whatever our given information is. So we're starting with a 1.23 gram sample of pyrite. We want to know how much sulfur is in there. All right, so you want to be very careful about labeling units when you do this, or any type of problem, because it helps you figure out what you need and what order to do things in. So we have 1.23 grams of pyrite, and we want to convert the mass of pyrite into the mass of sulfur, and determine how much sulfur is in that pyrite. So what we're going to do is use these two masses, which are related to the mass percent, as a conversion factor. We know that if we have 50 grams of pyrite, that's going to contain 26.7 grams of sulfur. And by just looking at unit analysis, we see that grams of pyrite cancels out, divides out. Canceling is not really a real mathematical operation, obviously. Grams of pyrite divides out, and we're left with grams of sulfur, which is what we want to solve for. So now we know that we can stop. We don't have to do any additional steps. And what we come up with when we do this numerically is 0.659 grams of sulfur, which corresponds to choice A. All right. So we can use mass percentages or ratios as a conversion factor. Alternatively, we could have found the percent, which would be, as we saw in the last problem, the percent for sulfur would be about 53%, 53.4%. We could have used that as our conversion factor, which would be 53.4 grams of sulfur per 100 grams of pyrite. There's a couple ways you could have approached this. This one we didn't have to do any additional steps. We could just use the given information, use the ratio directly. So we can also use mass ratios or mass percents as conversion factors. And so that's another important thing that comes out of this and allows us to determine the composition of samples of compounds that are different, different amounts. All right, so you will likely see homework problems that involve this concept, using mass ratios as a conversion factor. And so the way it works conceptually is that if we have a simple compound with two elements A and B, that can combine to form some compound, we can use mass ratios to really interconvert between any of these quantities. All right, so if we want to know, in this case, we knew how much We use the mass of the element and the mass of the compound together. It's also possible to figure out how much of each of the element will be present. So if we had instead said that there was 1.23 grams of sulfur, how much iron is there? A lot of different variations here, but it's all just using mass ratios, which are ratios of masses of elements in a compound, to do that. So you'll see a lot of those on the homework, and it's kind of the first type of, quantitative problem that we have to be able to do in this course. All right, questions on that before I move on to the last mass law? Okay. So the last mass law is the most complicated of them. It's not too bad, but there's just not a real friendly way to write this one out. It's kind of wordy, kind of verbose. But it's the law of multiple proportions. So as it turns out, we've talked about a few different types of compounds in this course already, and very often it's possible to take two elements, or even more than two elements, but let's just say the simple case of two elements, you can combine them to form more than one different compound. So we saw in that example that iron and sulfur combine to make pyrite, but it would be possible to also combine iron and sulfur in a different ratio to make a different compound. The example that you're probably familiar with already from your daily life is carbon monoxide, carbon dioxide. Those are both compounds of carbon and oxygen. Those are the only two elements, but they are combined in two different ratios to give you two different compounds. And that's what the law of multiple proportions deals with. It deals with the possibility of two elements combining to make two different compounds. And it's stated in a sort of quantitative way, which is that if 1 gram of element A combines with element X, so two different elements, as I'm abbreviating them, A and X, and let's say it's possible to form two different compounds. So in order for this to happen, this 1 gram of A is going to combine with two different amounts of X to form those two compounds. You're not going to have typically two compounds that have the same mass ratio, although that is still possible, but for this law we're excluding that possibility. But the two different masses of X that combine with A are going to be whole number ratios of each other, or very small ratios of each other. All right, so here's some examples of those ratios. So let's say 1 gram of A combines with 2 grams of X to form one compound. One possibility for how much it combines with to form the second compound would be 1. So it'd be like, for example, 2 to 1, or 3 to 1, 3 to 2, so on. Small whole number ratios that are going to be involved with this when one element combines with an element to form two different compounds. So this law is, if you're trying to recognize, when it applies, there's going to be a lot of conceptual questions on the homework and tests that, that ask you, which mass law is demonstrated by the following observation. If you're talking about law of multiple proportions, you're always talking about two or more different compounds. That's sort of the dead giveaway for law of multiple proportions. And let's look at sort of an illustrative example of how this works. So again, like I said, the definition is kind of wordy and hard to understand by itself. So let's look at some real data and see, using what we already know, how this plays out. So one example of law of multiple proportions is if we combine iron with oxygen, we can form two different compounds. Actually, there's way more than two compounds, but these are two of the compounds you can form when you mix iron with oxygen. The one that you're all familiar with is rust. Especially if you grew up in a northern state, you would see all kinds of rust on your cars during the winter time. And that's a mixture of iron and oxygen with this mass ratio of iron and oxygen. So these are the basically the mass percentages of each element. And then there's another compound called ferrous oxide, which is a black powder, so clearly distinct from rust, looks a lot different, has a lot of different properties. And in that compound you have also just iron and oxygen, but the mass percents are different. And so whenever you form two different compounds, you're going to have two different mass percentages involved. And so this is what law of multiple proportions tells us. And what it tells us even further is that if we take the ratio of, let's say, oxygen to iron or iron to oxygen, however we choose to do it, the two ratios for the two compounds will be related to each other by small whole numbers. Let's see how that works here. So if we have ferrous oxide, first compound here that we're dealing with iron and oxygen, let's figure out how much oxygen would combine with 1 gram of iron. And so the way we do that is we just divide the two mass percents. If we want to know how much oxygen is there for every 1 gram of iron, we divide the two mass percents. And so for ferrous oxide, that's 22.27 divided by 77.73. So when we divide the two mass percents, which are numbers out of 100 grams, this will tell us the ratio of the two elements in the compound, which comes out to 0.2865. So this number tells us, what this ratio tells us is, if we used 1 gram of iron, we would combine that with 0.2865 grams of oxygen to make this black compound ferrous oxide. Now let's do the same thing for rust. Take the mass of oxygen divided by the mass of iron, which we can just use the mass percents as a surrogate for that, since those are the masses contained in 100 grams. In this case, it's 30.06 for oxygen for rust, 69.94, and that comes out to 0.4329. So that means if we want to take 1 gram of iron and convert it into rust, we would need to use 0.4329 grams of oxygen. Yes? Probably. Yes, thank you for pointing that out. That should be a 2.7. So these numbers here are just these mass percentages read directly off, which I clearly failed to do the first time. But those are those two numbers, and those are the two numbers for rust. Okay, so you just divide those two numbers, and that's going to normalize things and tell you how much oxygen combines with 1 gram of iron when you have iron in the denominator here for both of them. And then if we take the ratio of those two ratios, we'll put the bigger number on top to make it a number greater than 1. So these are the ratios of the masses. It comes out to 1.500, which can be written as a simple whole number ratio of 3 to 2. Okay? And so this is a demonstration of law of multiple proportions. We've combined iron with two different amounts of oxygen to make two different compounds, ferrous oxide and rust. And when we take the ratio of those amounts, it comes out to a simple whole number value, 3 to 2. All right, you're never going to get some wild number like 1.00678 or whatever. It's always going to be a relatively simple number that can be thought of as a ratio of two small whole numbers. And that's what the law of definite proportions tells us. So there's a lot to take in there, and you'll have to spend some time on your own working through that, but keep in mind, from a conceptual standpoint, the law of multiple proportions always deals with two or more different compounds. That's sort of the dead giveaway there. All right, so let's do a quick review of the three mass laws. Normally this was I taught the class with 3 one-hour sessions last time, so this was 2 different lectures. So we're going to review something we just learned 10 minutes ago, but let's just summarize them all on one page. So we have the 3 mass laws: our conservation of mass, law of definite composition, law of multiple proportions, and as we saw, conservation of mass is probably the easiest one for us to appreciate, or one that we've not either. That's one that we were probably introduced to at a very young age, conservation of mass. And so during a chemical reaction, mass is neither created nor destroyed. Okay, so that's law of conservation of mass. Law of definite composition tells you about the composition of a single compound by itself, a single pure chemical substance. And each distinct chemical substance, pure substance, has a specific proportion of elements by mass. Now, as we'll learn later on in the course, and to give you a little bit of a teaser, there are obviously other ratios of elements, namely the mole ratios that you may have heard of in chemistry in high school or earlier in your life. Those are the more important ratios. We'll get to those later on. These are all of the very early laws of chemistry, which they had no concept of the mole at that time, and they were based on relatively simple observations that involve weighing substances, one of the simplest measurements we can make. So all of these early laws, as the name suggests, deal with mass. And so this definite proportional law is constituted in terms of mass. There are other types of atomic or elemental ratios that we'll talk about later in the course as we refine our definitions. And then finally, the law of multiple proportions, the confusing one that we just ended with. Remember, the key idea here is that we're talking about two different compounds formed from the same two elements. So if two elements combine to form multiple compounds, all right, so we're talking about multiple compounds with the same elements in them, but in different ratios. Each compound will have a distinct mass ratio. So that's how we sort of distinguish the two from each other, or at least one way to distinguish the two. And the ratio of these two ratios, so we're talking about again the ratio of ratios, which is a weird way to think of things, but that's what it is. The ratio of these two ratios will be small whole numbers. Or a simple fraction. All right, in other words, you can't just combine two elements in any random ratio that you want to make different compounds. There are always going to be sort of discrete ratios that are involved, and the relationship between those ratios are very simple whole numbers. So these are the three mass laws, and then what, and as I said at the very beginning, when you have a set of laws, you want to use a theory to explain the laws. So why do these observations hold true? These are all based on a bunch of experiments, a bunch of observations that people made, and what's the proposal for how this works? And so the unifying theory that explains all of these laws is Dalton's atomic theory. And so this really gets down to the microscopic level to try to understand what's happening at that level, at the particle level, to explain why we have these very distinct observations involving the masses of substances in chemical reactions. So Dalton's atomic theory, depending on how you break it down, has a few different postulates involved with it. And so the first one is that substances are composed of tiny particles called atoms. All right, so this was, as I said, not a brand new idea, but an important suggestion of this theory is that these atoms cannot be decomposed any further. So that's one important part about atoms. You can't break them down any further. That's sort of the simplest building block of matter. Or I like to think of atoms as sort of the Legos that make up all of the substances that we have in our daily lives. So they're the simplest form of that. And then another important thing about atoms is that they cannot be converted into different types of atoms in a chemical reaction. At the very end of Chemistry 2, Chem 1332, you'll learn about nuclear chemistry, which sort of shows that this isn't 100% true, but in a chemical sense, in a chemical reaction, you can't convert one atom into a different type of atom. Or another way of saying that is that elements cannot be interconverted. Okay, so if you react iron and oxygen with each other to make those compounds we just talked about, whatever product you make will only have iron and oxygen in it. You're not going to react iron and oxygen and make something that has gold in it. And that's sort of where the idea of the alchemist sort of breaks down. They thought they could change lead into gold. In reality, that's not possible. and this is what one of the parts of the atomic theory tells us. All right, another important part of the atomic theory is, what's the difference between the atoms that make up each element? So we have all these different elements. Even more and more are being discovered today. Although the ones that are being discovered today usually persist for about, I don't know, a femtosecond or something. So they're not exactly useful substances, but they are more being discovered. And even the naturally occurring ones took a long time for us to discover all of them. And what's the difference between all of those different elements? And the difference is that, and this is what the atomic theory tells us, and this is the part of the atomic theory that's not 100% true, as we'll start to see next time. But what it says in the atomic theory is that the atoms of a given element have the same mass and other properties. And that they are distinct from other elements. All right, so in other words, the atoms that make up iron are going to be different in mass and in other features from the atoms that make up oxygen, and so on. Now, just to let the cat out of the bag, the one part of this that's not 100% true is that all of the atoms of a given element do not necessarily have the same mass. We'll talk about that next time. Those are called isotopes. But they do have some distinct properties and other features that are unique for that element. So it's not 100% wrong, this statement here, but it's a little bit too simple. But that's one of the parts of Dalton's theory. And then finally, the last one, which we kind of already should appreciate, is that chemical compounds are formed when atoms rearrange or combine, I guess is a better way to say it. And these chemical reactions involve reorganization of atoms. And this last one is especially important for explaining the last two mass laws, which is, why do substances have definitive mass compositions, and why do two different substances, why are their compositions related by simple whole number ratios? It's because you can't have a fraction of an atom. Atom is the smallest building block. If you combine, so for example, the example we gave you before with iron and oxygen, ferrous oxide, that first compound is one atom of iron combining with one atom of oxygen. And so discrete numbers of atoms combining to make that compound. The other compound, rust, is two atoms of iron combining with three atoms of oxygen. So there are always these discrete whole number ratios of the atoms that combine, and then that translates on a macroscopic level to the ratios of the masses that are involved in a much larger sample of that compound. So the point is, you have these discrete building blocks called atoms. You can't have a half of an atom or a fourth of an atom. They always have to combine with each other in whole number ratios at the microscopic level, and then that translates into some of the mass observations that we see at a higher level. All right, and then finally, the last thing I want to do about the early laws are, how do we determine what chemical formulas are? What were some of the earliest ways we did this? So we now know that water has the formula H2O, but how did the early chemists even decide that that was the correct ratio? They knew the mass ratio in water, that could be measured, but how did they then translate that into an atomic ratio of 2 atoms of hydrogen, 1 atom of oxygen? So this came from really two important scientists, Gay-Lussac and Avogadro. All right, so Gay-Lussac made this following observations. If you have two gases at equal temperature and pressure, we will talk a lot more detail about these things later on, so we just need to get the really basic level details for now. At equal temperatures and pressures, gases combine in chemical reactions in fixed whole number ratios. All right, so again, this is a macroscopic observation, something that he made on large samples of gases. So if you have 2 volumes of hydrogen, 2 liters or 2 gallons or whatever volume is your favorite unit of measure, if you had 2 volumes of hydrogen and you're going to combine that with oxygen to make water, that would always combine with 1 volume of oxygen. And then the water vapor that you form would be 2 volumes. Alright, so if this is 2 liters of hydrogen, it would react with 1 liter of oxygen, and that would form 2 liters of water. So that was kind of, again, a macroscopic observation. And the person that interpreted this was Avogadro, whose name you probably heard before. He actually didn't discover his own number. It was just named after him. But he discovered or came up with this interpretation, which is that if you're talking about 2 gases at the same temperature and pressure, equal volumes of those gases, even if they're 2 different gases, have the same number of particles, which particles being atoms or molecules. Alright, so what that led to was the idea then that this macroscopic observation, 2 volumes of hydrogen, 1 volume of oxygen making 2 volumes of water vapor, could be also thought of at the atomic level as 2 atoms of hydrogen combining with 1 atom of oxygen, and that gives us 2 molecules of water. And so these, in other words, these volume ratios that we observe are exactly equivalent to what's happening at the microscopic atomic level. Okay? And so his interpretation allowed that. And so then by keeping close track of the ratios of how gases combine with each other, you can then determine the exact chemical formula of a gas molecule, which in this case would be 2 hydrogens, 1 oxygen, H2O. All right, so that allows that to be interpreted. Yes? I think where I'm confusing myself is, yeah, that's, if I'm writing it this way, I should say it that way. Now, the reason that that picture is not 100% accurate is because in reality, hydrogen and oxygen exist as diatomics. And so if we want to look at this sort of picture again, 2 volumes of hydrogen, 1 volume of oxygen, making 2 volumes of water. So what's happening here in reality is that most of our gases, as we'll learn later on, are diatomic, which means that the elements are not simple atoms. They're 2 atoms connected to each other, H2, O2, Cl2, and so on. So when we have 2 volumes of hydrogen, we have, at the simplest level, 2 hydrogen molecules. And then that combines with 1 volume of oxygen, which would contain 2 of the, just 1 O2 molecule. And that makes 2 volumes of water, which would be 2 molecules of water. Okay? Let me color code this a little bit better because I'm actually not confused about how this works. Alright, so oxygen in red, hydrogen in blue, and when you combine them with each other at the macroscopic level, it's a 2-to-1 ratio, gives you 2 volumes of water, and at the microscopic ratio, the same thing happens. And then if we did a different gas, let's do hydrogen this time with chlorine, what we find is that if we react 1 volume of hydrogen with chlorine, they combine in a 1-to-1 ratio this time. Change shows the color again so you're not confused. So chlorine will be green. So if you combine hydrogen with chlorine, they combine in a 1-to-1 ratio, and what you get then is a molecule that has just one of each instead of a more complicated ratio. So you have one hydrogen and one chlorine connected to each other to make your 2 volumes of hydrogen chloride. All right, this is sort of a weird time in the course to introduce this concept because it's something, as I said, we'll get in more detail later on. But it's in your chapter 1, and the reason being that these were the types of experiments that people did to understand the ratios of elements and compounds. You don't really need to understand it at any level deeper than that for now. We'll come back to these gas laws later on. But this is how people figured out the ratio of different elements in gas-phase compounds, recognizing that the volume ratios correspond to the ratios of the atoms or molecules that are reacting with each other or forming. Now, the last thing I want to close with in the remaining time here in these last 3 slides is sort of the atomic picture of the element, the microscopic picture of the atom itself. So now that we know that atoms make up substances, what are more details about the structure of those atoms? And this is an idea that came about much later. So a lot of these early mass laws were done back in the 1800s, but for a long time people didn't really know what was the structure of an atom. Is it just a amorphous blob of substance? Does it have subatomic particles, smaller things that make it up? How are those things arranged, if they are there, and so on? And so there were a few key experiments that allowed us to identify the different parts, the constituent parts of atoms. And the first one was the cathode ray experiment. And so what you're doing here is you're setting a very high electric current through a piece of metal, usually. And then you have these 2 plates here generate a large electric field. And you see a beam that comes off of this metal and it's deflected by the electric field. So that's why it's shown here as being bent. Now the person that did this was J.J. Thomson. It's always amusing to me that these early scientists who made some of the greatest discoveries ever all look so unhappy. And this is one of them. And anyway, what he found was that these things that he called cathode rays, he found that they were repelled by the negative pole of an electric field. All right, so in this picture then, I guess this would be negative side electric field, this would be positive. And so the rays always were repelled by the negative side, meaning that they also have a negative charge. And he called them electrons. The negatively charged part of an atom was called an electron. And they could be produced from many different substances. All right, so it wasn't just one metal that gave this. If you use a bunch of different metals, a bunch of different substances, he could produce these cathode rays, these negatively charged electrons. And from this, he concluded that all atoms have electrons, which we now know is 100% true. And finally, what this experiment also determined was the charge to mass ratio of the electron. It could not determine the absolute charge or the absolute mass, but it did show what the ratio of those two was in the electron. Okay, so he found that there was this negatively charged subatomic particle that's part of the atom, and it was produced by a bunch of different materials, and it's definitely negatively charged. That was sort of credited as the discovery of the electron. And then the other key experiment dealing with electrons was the oil drop experiment. Okay, and so this was done by another unhappy fellow named Robert Millikan. So Robert Millikan was the oil drop experiment. And so what he did here was he generated a bunch of negatively charged oil drops. So he took these really small drops of oil, he subjected them to a very large electric field, which caused some of them to be negatively charged, and then he watched as those drops fell, and he increased the electric field that they were falling against. And at some point, those drops would float because the electric field was strong enough to repel the negative charge and sort of hold them in place. And he knew the mass of the drops, and he knew their charge and all that stuff. So there's a lot of physics here that we're not going to go into details of, but that's kind of the setup of his experiment. And our more important thing to learn is what are the key observations of this. So these falling negatively charged oil drops were stopped by an electric field. And what he found was that the charges always occur in regular whole number intervals. So he was able to measure the charge of the oil drops based on how strong the electric field was that was needed to stop them from falling, basically. And he found that these charges, not all the drops had the same charge, but again, they were related to each other by regular whole number ratios. So that lended further support for the idea that there are these discrete negatively charged particles called electrons, which Thomson proposed in his cathode ray experiment. This was further support for that. But even more importantly, this allowed us to determine both the mass and the charge of those electrons. All right, and so I think I'm running out of time. I want to do maybe one more thing, if you'll bear with me. And the last thing I'm going to talk about is what was sort of the early picture of the atom. So we're going to talk about why this is wrong next time. But what Thomson came up with also was an early picture of the atom. So if there's negatively charged particles in an atom, there must also be positively charged particles because the charge on the atom is 0. So there has to be something positively charged to balance that. And so the early picture of the atom that was proposed was the plum pudding model, which is where you have your discrete negatively charged electrons and they're floating around in sort of this diffuse sea of positive charge. Okay? So the idea from the plum pudding model was that atoms consist of electrons and that these electrons are held in place by a diffuse cloud of positive charge. And that the electrons are just randomly embedded into this positive charge. There's really no structure involved with them. Now, like a lot of the early atomic theories, this was dead wrong. And we're going to talk about why that is next time. But it was sort of the important starting point, sort of the hypothesis that people started with when they were further investigating the structure of an atom. And that's what we're going to talk about starting next time as we deal into more details about the structure of the atom. All right, so I will see you on Wednesday. And enjoy your next couple days. And if you have any questions, come up and see me afterwards. Sorry, I'm having trouble with this.